السلام عليكم ورحمة الله وبركاته. Sharing my screen. All right. Let me take it to presentation mode. First of all, I couldn't deliver my lecture yesterday because I wasn't feeling fine. However, I will still make it up. Okay. Remember now, we have a total of about 6 hours to make up. So I'll gradually make up lectures and upload. Okay. I will let you know about the time so that those that are available can join me. Okay. If you remember in my last class, we started discussing briefly about fluid statics. Okay. Fluid statics deals with problems associated with fluids at rest. Fluid statics, so it's the static of fluids that, dealing with the statics of fluids. Okay, fluid statics is generally referred to as hydrostatics when the fluid is a liquid, and as aerostatics when the fluid is a gas. Gas. Okay, hydro generally water. Okay, because normally our fluid is water most of the time, most especially civil engineering. Okay? In fluid statics, there is no relative motion between adjacent fluid layers. And thus, there are no shear stresses in the fluid trying to deform it. Because the fluid is at rest, so there is no motion between adjacent layers. If there is no motion, then there is no tangential stresses. Okay? But there is only one stress, no tangential stress, but normal stress exists. Okay? The only stress we deal with in fluid statics is the normal stress, which constitutes the pressure, isn't it? Or which is essentially the pressure. The normal stress is the pressure, okay? Which is the pressure, and the variation of pressure is due only to the weight of the fluid, as we explained before. When you have a liquid or fluid that is at rest, the variation of pressure is only due to altitude. Okay, altitude. Okay, it varies due to altitude, and here altitude will imply that the weight of the fluid increases or decreases, isn't it? The force exerted on a surface by a fluid at rest is normal to the surface at the point of contact, and there is no relative motion. So this is still emphasizing about the normal stress, okay? And the fact that the fluid is at rest, and that fluid statics is used to determine the forces acting on floating or submerged bodies. The forces developed by devices like hydraulic presses and car jacks. Okay. We already have seen some examples of using the car jacks, So we determine the forces on floating or submerged bodies. Submerged means the body is inside water, okay? It's completely immersed in water, that is submerged. Okay? The design of many engineering systems such as water dams and liquid storage tanks requires the determination of the forces acting on their surfaces using fluid statics. You need to know the forces so as to know the resultant hydrostatic force or pressure force. Okay, so that will now enable us to design for the support system, okay, adequate support system. Okay, you need to know the hydrostatic forces are acting, okay, or the resultant hydrostatic force in particular. When you have dam, when you have storage tanks, all these so huge volumes of liquid, okay? So, and these liquids exert, huge hydrostatic forces on the supporting materials, okay? So the analysis of forces acting on these water structures or, hydraulic structures, is very, very important so that we can adequately design the support mechanism or the support system for such structures. Complete description of the resultant hydrostatic force acting on a submerged surface requires the determination of the magnitude, the direction, and the line of action of the force. The force is being a vector, we need the magnitude, the line of action, as well as the direction. Okay, this is the complete description of any vector quantity, force being one of them. Okay? And hydrostatic force is simply the pressure force. Okay, hydrostatic force and pressure force are synonymous, so I'll be using the two terms interchangeably. Okay, hydrostatic force, pressure force. Static, like I said, this will okay, so this is the same slide. Okay, hydrostatic forces on submerged plane surfaces. Now, a plate, I made mention of, we'll study either floating bodies or even bodies fully submerged in water. Okay, a plate such as a gate valve in a dam, the wall of a liquid storage tank, or the hull of a ship at rest, all is part of the ship. The outer part that is in contact with water, either completely submerged or touching the water. That is the hull of a ship. Okay, all this, they are subjected to fluid pressure distributed over its surface when exposed to a liquid. Valve in a dam, the wall of a storage tank. You see, this is a dam, as you can see. Okay, this is a dam which is holding water. The reservoir is downstream. Okay, so this is like the wall of a dam, a very huge one called Hoover Dam in the United States. Now, still on the hydrostatic forces on submerged plane surfaces. On a plane surface, hydrostatic forces form a system of parallel forces. This is a plane surface. You can see it like a retaining wall. Okay, like a swimming pool. All this can be visualized like a swimming pool, the walls of the swimming pool, or any underground tank. Either carved, whether you dig ground and make like a reservoir. Okay, or you can visualize it just like a retaining wall, let's say in a swimming pool, let's assume. Okay, so on the plane surface, the hydrostatic forces form a system of parallel forces. Okay? These are the parallel forces. Okay, although these are the pressure force, the pressure acting on both sides. Okay, and we often need to determine the magnitude of the force and its point of application, which is called center of pressure. The center of pressure is the point at which hydrostatic forces are applied. And in most cases, the other side of the plate is open to the atmosphere. Like in this case, this is the other side, which is open to the atmosphere. So you have atmospheric pressure acting on the right side as well as on the left side. Okay, so it's acting on both sides, hence it cancels out. Okay, so in most cases, the other side of the plate is open to the atmosphere, such as the dry side of a gate, and thus atmospheric pressure acts on both sides of the plate, yielding a zero resultant. Yielding or giving a zero resultant because they are equal and opposite. Okay, so they will cancel out. And this is when we consider the atmospheric pressure. This is the pressure force, which is the pressure is increasing with depth. Okay, you can see that it is atmospheric at the top. Okay, so from here to here is atmospheric pressure. Okay, and then when you go deep down, it increases. So this is showing the increase in pressure. Okay, which is acting on this plate, this plane surface. Okay, and this total pressure at the bottom now is atmospheric pressure plus the gauge pressure. Rho G8 is the gauge pressure due to the height of water, okay, which decreases as you go up and increases as you go down. So since the atmospheric pressure are equal, the atmospheric pressures acting on both sides are equal and opposite, so they cancel out and we can eliminate the atmospheric pressure. Okay, so that's why here we remove the atmospheric pressure and use only the gauge pressure. So here we subtracted the atmospheric pressure. Okay, and this gives only the gauge pressure. That's the pressure above atmospheric. It's above the atmospheric pressure. So in such cases, it's convenient to subtract the atmospheric pressure and work with the gauge pressure only, as I explained here. Okay, for example, the gauge pressure is just rho GH at the bottom of the lake. Okay? So these two systems are the same. Okay, this first system is equal to the second system. Okay? We subtract the atmospheric pressure, but if the pressure here is not atmospheric, then is going to be different. Okay, or if the liquid here, if the fluid above the water is also not atmospheric, maybe another gas at different pressure or liquid also, then we just cannot subtract the atmospheric pressure this way. We have to consider the particular pressure acting. Okay? We'll expatiate this as we move on. And forces on plane surfaces, this is a case we're examining this when you have uniform pressure distribution. Okay, if to say, let's say like in this case, if you consider this plane surface, the bottom, okay, there is uniform pressure acting. Okay, the pressure acting is uniform. Okay, in this case, it's uniform at every point. Okay, so this is like the pressure distribution here for the horizontal plate. Okay, but for the vertical one, because it increases with depth, it is not the same at every point, but it is uniformly varying. For the horizontal one, because the plate is at the same elevation, then the pressure acting is the same. Okay, pressure varies only with elevation. This we explained before. So this is like a case when you have uniform pressure distribution. The arrow, the length of the arrow represents, the pressure. Okay, the pressure force in particular, or the hydrostatic force acting on the plane surface. Okay, and this uniform pressure distribution can be reduced to just a resultant force acting at the center of pressure. Okay, resultant force acting at the center of pressure. Okay? In this case, the center of pressure is equal to the center of gravity. Okay? In this case, and this also is true when you have horizontal plate. Okay, horizontal plate. Okay? The center of the resultant force or the resultant hydrostatic pressure is acting at the centroid of the plate as well as the center of pressure. But as we are going to see later, if it is inclined plate or vertical plate, usually the center of pressure do not coincide with the centroid. Like in this case, the centroid of this plate is somewhere here. Okay, this is where the centroid is. The center of pressure, going by the pressure distribution, you will agree with me that the resultant hydrostatic force will be acting not at the centroid, but somewhere here. Okay, somewhere here. Okay, so this will now be the center of pressure, CP, which is designated with plus sign, then cycle around it. This is the center of pressure. So for vertical and inclined plates, the center of pressure do not coincide with the centroid of the plane surface. But for a horizontal plate, when you have a uniform pressure distribution, when you have a uniform pressure distribution, then the centroid of the plate coincide with the center of pressure. Okay. So like in this case, the center of pressure and the centroid, they coincide. Okay, and the line of action of the resultant force passes through the centroid. Okay, like I say, for a vertical plate and inclined plate, this is not the case, and this we are going to see later. So now forces on plane surfaces. Still, now the previous case was a case when you have uniform distribution. This one, you have pressure distribution that is varying, that is non-uniform. Okay, so here you have, this is the plate, okay, which is inclined. You can see the pressure distribution, increases linearly. Okay, highest at the bottom and minimum at this point, at the lowest elevation of the plate. Okay, and now to represent this hydrostatic pressure distribution, this is the centroid of the plate, but the resultant pressure force passes through the center of pressure, which is different from the centroid. This is the centroid and this is the center of pressure. Okay? So the center of pressure is below the center of gravity, or centroid. Okay, so the center of pressure is below the center of gravity. And the symbol for the CP is a cycle with a plus symbol inside. Okay? So later we will find out, we already know how to find the centroid of any surface. This we learned in statics, okay, I think chapter 9, yeah, chapter 9 of statics, CE 201. We learned how to find the centroid of a plane surface, and what have you. So now we will learn how to find the center of pressure. Okay? The center of pressure, that is the point where the resultant hydrostatic force passes through. Okay, or the resultant pressure force passes through. Okay, center of pressure. Now, force caused by a hydrostatic pressure distribution. So this is where we are going to determine or to derive the formula for center of pressure. Okay? Before doing that, we will also establish the pressure force or the hydrostatic force, the formulation for the hydrostatic force with respect to area and the pressure acting. Okay, so here we will derive the force and its line of action. So this is like any arbitrary body of any given area submerged inside water. This is like the side view. Okay, this is like the plan. Okay, this is like the plan, and this is like the side view, AB. Okay, the body is completely submerged in fluid or water. Okay, then you have the centroid here, and you have the center of pressure, which definitely is not going to coincide with the centroid because the plane surface, the panel is inclined. Okay, if as I mentioned to you that if it is inclined or vertical, then center of pressure and centroid do not coincide. They coincide only if the plane or the plate is horizontal. Okay, if it is horizontal, then you have uniform pressure distribution acting. If it is vertical or inclined, the pressure distribution is not uniform, meaning it is not the same at every point on the surface area. Okay, that is why you can see it is increasing. It increases as you go deeper down. Okay, because pressure increases with depth. So this we consider a slanting height. It is slanted, by an angle alpha here. This is the slanting angle. And from O here, you have the centroid, Y bar. You have the center of pressure, Y subscript CP. And we consider a small element, dA. And we want to find the pressure force acting on that element. And then we integrate to find the total pressure force and its line of application, which is capital F here. Okay. So to begin with, to find the pressure, E equal rho gamma y sine alpha. I will explain all that. Okay. So here we derived before, the differential equation of the pressure force, that it is equal to minus gamma delta z. Okay. Pressure force is minus gamma delta z, and here delta z is the vertical distance. Okay. Delta z in this case is the vertical distance. So if you consider this small element, whose distance from O is y, so what is the vertical distance? Okay. The vertical distance to this point, okay? If we draw a horizontal line and a vertical one, this is 90, so this is delta z, okay? And this is y, so the hypotenuse is y. Okay? And this angle, okay? This angle is alpha, okay? So what is sine alpha here? Sine alpha is opposite over hypotenuse, isn't it? Delta z over y. So y is equal to, delta z is equal to y sine alpha. And delta z is the height, isn't it? So our pressure is now gamma y sine alpha. Okay? Minus is to indicate that the pressure increases when z decreases. Okay, that is simply why we have the minus sign. Okay, so that's why we have the pressure here, gamma y sine alpha. Gamma is unit weight, the unit weight of the liquid. Okay, unit weight of the liquid. So that is how we obtain this equation. Okay. Now, still, the force due to pressure is given by, here we are considering this small element dA. Okay, this small element here, dA. So the force, the pressure force, that is F subscript P, that is the pressure force, is the integral of the area, okay, P dA. Pressure is force over area. So the hydrostatic force over area. So the hydrostatic force is the pressure times area. Okay. So this is P dA. dA is because we are considering small elements dA. Okay. The pressure can be found using the hydrostatic equation, okay, which is P now. So P is this we already derived, because delta Z is Y sine alpha. Okay. And then substituting P here as Y gamma Y sine alpha. Okay. Y sine alpha is constant. Only thing that changes is Y, isn't it? That is because this is like an arbitrary area that we have chosen. So an integral of y dA is what we call the first moment of area in chapter 10. Chapter 10 of statics. If you remember chapter 10, where we discuss moment of inertia, first moment of area, second moment of area. Okay, so this is called the first moment of area. And the first moment of area simply gives the centroid. Okay? Here, integral of y dA, okay, the first moment of area, and its equivalent, if you remember the centroid, y bar is given by y dA over A. Okay, this is the formula which we learned in statics. That's why statics is a prereq to this course. Okay, this is how we calculate the centroid. Okay, integral of y dA divided by the area. Okay, So now, if you have integral of y dA, it will be equal to y bar, which is the centroid, times the area. So we are now replacing integral of y dA with y bar A. Okay, so we remove integral of y dA and substitute of y bar A. Okay, and we rearrange, we remove the area. So this is simply pressure, average pressure, the centroidal pressure acting at the centroid, okay, because it's acting at the centroid because of this y bar, okay, and this is the area. Okay, so we have F, the hydrostatic pressure, equal the pressure at the centroid of the area times the area. Okay, this is very important. For an immersed body that is either vertical or that is inclined, okay, the hydrostatic force is acting is equal to the pressure acting at the centroid times the area of the plane or of the panel. Okay? This is very important. Okay, this is not just the air, but the pressure that is specifically acting at the centroid of the panel. Okay, so this equation shows the hydrostatic. Okay, so the equation shows the hydrostatic force on a panel of arbitrary shape. It can be rectangular, elliptical, or anything. Okay, and it's given by the product of the panel area and the pressure at the elevation of the centroid. Okay, the pressure at the elevation of the centroid. We'll take some examples to demonstrate this. Now, having established this, having established that the pressure force or the hydrostatic force acting for submerged panel is given by the product of the pressure acting at the centroid and the area of the panel, then we have to go a step further to find the center of pressure. Okay, to find the center of pressure. And to find the center of pressure for a hydrostatic pressure distribution, here for the panel shown to be in moment equilibrium, the torque is moment. This also we learned in statics. Okay, torque, a moment. I mean, it's one of the equilibrium equations. Okay, we take moment with some forces, the sum of all forces equal to 0, and the sum of all moments is one of the conditions for static equilibrium of a body. Okay, that the sum of all moments must be equal to 0. Okay, so the same thing here. For the panel to be in equilibrium, meaning for it to remain static, to remain as it is without any movement, the moment equilibrium has to be considered, and the torque, which is the moment due to the resultant force, must balance the torque due to each differential element. Okay? If you look at this, this is the pressure force acting, Fp, isn't it? F subscript P. So the pressure force due to the resultant pressure force acting at this point is equal to the pressure force, is equal to the moment due to the individual elements. Okay? Due to the individual element acting on the body, that's dF. Okay? And what we're saying is when we take moment about the centroid, when we take moment about point O, the moment is going to be force times distance. Fp is the pressure force times the distance YCP. Okay, and this is equal to the moment due to the individual elements, which is YDF. Y is the arbitrary distance for any small element, and DF is the small pressure force acting on that element, similar to what we have on this element DA. Okay, the pressure force acting on it is DF. Okay, so when we add the moments about O, they should be the same. That is YCP times the resultant pressure force is equal to the integral of the individual small pressure forces DF acting times the distance of that small element to the point of reference. Okay, so the moment at O is Fp, yeah, times the distance YCP. This should be equal to the sum because integration is the sum of all the moments due to small elements dA. Okay, and the distance to the point of reference O here is Y, so, and the pressure force acting is dF. This is simply what we have. The remaining is just to make some substitutions. Okay, YCP here is the slant distance, okay, from the center of pressure. If you look at YCP, is slant. That is like inclined. It is inclined. Okay, that is what is meant by slant. Okay? It is the inclined distance from the center of pressure to the surface of the liquid. Okay, and this and denotes the distance measured in the plane that runs through the panel. It runs through the panel, and the differential force dF is equal to PdA. Okay, because the pressure force is the pressure acting at the on that area times the area, which is dA in this case. Okay, so now substituting dF as PdA, we have this. Okay, PdA, and then remember we know what is our P before. P is given by gamma y sine alpha, so we substitute it here to have this. Then gamma is constant, sine alpha is a constant, so the angle doesn't change. Okay, then we are left with y squared dA. And this is also second moment of area or moment of inertia. Okay, remember the moment of inertia in chapter 10. Okay, moment of inertia. Okay, the second moment of area. Okay, is integral of y squared dA. Okay, now the second moment of area, or the area moment of inertia, is identified as I naught. And for engineering applications, it is convenient to express the second moment of inertia with respect to horizontal centroidal axis, like the parallel axis theorem. Okay. Here, because of the fact that this element is not at the surface, it's not at our line of reference, which is this line, we have to use the parallel axis theorem. This you also learned in statics. Okay, if you have, let's say this is xy, okay, and you have this rectangular body, so you can determine its moment of inertia about the x-axis, which is for rectangle, let's say, I think BD cubed over 12. Okay, now if it is not on the centroidal axis, you see here the axis, x-axis, through the centroid of the rectangular body. What about if it is if the rectangular body is at a distance? The centroid is displaced from the x-axis by a distance. Okay, it's displaced by a distance, say y here. Okay, what is the moment of inertia? Okay, the moment of inertia in this case, we use what is called moment of inertia through the centroid is I bar, which is and the moment of inertia at this point away from the axis of reference is now going to be the centroidal moment of inertia I bar plus the distance to the centroid y squared times the area of this area, the area of the body. Okay, so this is simply the parallel axis theorem, and this is exactly what we are doing here. Parallel axis theorem has been explained in statics chapter 10. So if you still want to review it, I reviewed it for you here, but you can go back to statics chapter 10 and see even the examples. Okay, so I naught here is given by the centroidal moment of inertia plus y bar squared. Y bar is the distance from the centroid, from the reference axis to the centroid of the body, which is here. You can see y bar is here. Okay, from the reference axis to the centroid of the plane surface of the plane object. Okay, so we have I naught to be I bar plus y bar squared A. Okay, so instead of integral of what y squared instead of integral of y squared dA, we substitute it with the centroidal moment of inertia plus y bar squared A. Okay? It's exactly what we did here. And then for force, we'll substitute for force as well. Okay, force we derive it before to be this, and we substitute it, and then from here, gamma will cancel out and sine alpha. Okay, sine alpha. So we make yCp the subject, which is equal to y bar plus I bar over y bar A. Okay, and this shows that the center of pressure is lower than the centroid because yCp minus y bar is a positive quantity. Okay, if it is positive quantity, it means yCp is greater than y bar, isn't it? If it is greater than y bar, then it means for an inclined plane, this is the centroid, the center of pressure is below the centroid. Okay, that is what this equation means. Okay? And that the center of pressure is dependent only on the geometry of the surface, that is dictated by the area and the moment of inertia. Okay, that is dictated by the area and the moment of inertia, and the depth of submersion, that is y bar, the depth to which it is immersed in water, which is y bar. Okay, so with this formula now, we can find the moment of the center of pressure. Okay? This derivation is very important, but the most important thing is the formula now and the application of the formula, which we are going to do in the next example. Okay? In this equation, the area moment of inertia is taken about a horizontal axis that passes through the centroid of the area. And you have the formulas for the moment of inertia presented in figure A.1. Okay? This is like for rectangle, for triangle, for different shapes. You can find the formula for different other shapes. Okay? And with this again, even if the body is vertical, we can apply the same formula, because if the body is vertical, all it means is that alpha is equal to 90 and sine alpha equals 1. Simple. Okay, this is for a slanting or inclined plane. For vertical plane, it means alpha equals 1. Simple. And alpha equals 90. That is what it means. Okay? And the formula for the center of pressure remains the same. Formula for the center of pressure remains the same. It is only formula for the hydrostatic pressure force that will change, because we will no longer have sine alpha. Okay, the hydrostatic force for a vertical plane will have F equal y bar A in this case. Sine alpha equals 1, because the inclination now is vertical. So alpha is 90 and sine 90 is 1. Okay, but the center of pressure remains the same. I mean, the formula for the center of pressure remains the same. Now, summary of the panel equations. Okay, first we have shown that the hydrostatic force acting on a panel immersed in water is given by the pressure acting at the centroid and the area. Okay, this pressure evaluated at the depth of the centroid and the area. Okay, and the application of the center of pressure, which is the point of application of F, the hydrostatic force. We use this formula. Okay, so this gives us the location of the center of pressure, which is the point through which hydrostatic force, the resultant hydrostatic force, is passing through. Okay, and this is like simple demonstration. Okay, this is like summarizing all that we did. The gauge pressure, is the centroid. This is the pressure force, resultant pressure force passing through the center of pressure. Okay, and assumptions inherent in these derivations. Okay, the problem involves only one liquid. We see, for instance, if we have more than one liquid, what happens? Okay, The pressure distribution is hydrostatic, meaning that the fluid elements are supported only by the hydrostatic pressure. The weight of the fluid element is supported only by the hydrostatic pressure. The pressure at the surface, at the free surface, is 0 gauge, meaning it's atmospheric. The panel is symmetric about the an axis parallel to the slant distance. Okay? So now, before we go to example, okay, I will still explain or again summarize, present a more pictorial form what I presented. Okay. For horizontal plate, I explained you have uniform pressure distribution, and the resultant hydrostatic force is passing through the same point. Okay, and the pressure force is simply, pressure acting. P naught is the atmospheric pressure. P naught is the atmospheric pressure. And A is the area of the plate. So this pressure, okay, PA. Okay. If we ignore the atmospheric pressure, then P naught is 0. Okay, meaning we work with only the gauge pressure. This will become important if we have another liquid on top. Okay, we will have to consider P naught, not equal to 0 in that case. Okay. Now, if it is horizontal, if it is inclined, which is the case, that is tilted. Okay, we have seen that resultant pressure force. This is also the atmospheric pressure. This is gamma rho g, and this is the distance to the centroid from the surface, the slant height. Okay, from O to this point, to the centroid of the object. Okay, which is S plus B over 2. Okay, which is simply y bar. Okay, which is simply y bar. Okay, and this is sine alpha, and this is A. This is simply similar to what we have here. Gamma y bar sine alpha A. Okay, gamma y bar sine alpha A. Okay? And then if it is vertical, like I said, we will not have, it is the same. Only thing sine theta will vanish because sine theta now is 90. The angle now is 90 degrees. Okay, and sine 90 is 1. So it becomes, the pressure force becomes this without sine theta. Simple. Okay. Now pressure prism, still understanding the how hydrostatic pressure acts on immersed body. When you have a surface, a plane, a panel, okay, you can see it, AB immersed in water. You have the water pressure acting on it. You note these arrows, okay, and it increases linearly, okay, given by the prism. The pressure acts normal to the surface because pressure is always acting normal to surface because it's due to the normal stress. Okay, pressure for the hydrostatic force is due to the normal stress. The hydrostatic forces acting on a flat plate of any shape form a volume whose base is the plate area and whose length is the linearly varying pressure. So the hydrostatic force acting on a plate volume forms a volume whose base is the plate area. This is the volume, the plate area, okay, and whose length is the linearly varying pressure. Okay. So this virtual pressure prism has an interesting physical interpretation. It's equal to the magnitude of the resultant hydrostatic force, okay, because this is, we integrate to find the resultant hydrostatic force, integral of P dA, because from here to here, this is the pressure, this is the area, okay? So when you multiply the area by the pressure acting, you get the total volume and integrate it over the area. Okay, and this gives the resultant hydrostatic force acting on surface AB or on plane AB. And the line of action of this force passes through the centroid of this homogeneous prism. The The centroid of the prism, not the centroid of the surface. Matthew. Because the centroid of the prism will be somewhere here. Okay? But the centroid of the surface will be above the centroid of the prism. Okay? Will be somewhere here. So this is the centroid of the surface, AB. This is centroid of the prism, which gives the center of pressure. Okay, and this is the center of gravity. Okay, so center of pressure and center of gravity coincide if the surface is horizontal. This I explained before. But if it is vertical or inclined, they don't coincide. The center of pressure is below the center of gravity. Okay, so is below the centroid all the time because of the formula that we derived earlier. Okay, so projection of the centroid on the plate is the center of pressure. Yeah, this is exactly what I finished explaining. And with the concept of pressure prism, the problem of describing the resultant hydrostatic force on a plane surface reduces to finding the volume and the two coordinates of the centroid of this pressure prism. Okay, so to find the resultant hydrostatic force on the plane surface, we are intending to find the volume. How do we find the volume? We find the volume using this integral of PdA, okay, and the two coordinates of the centroid of this pressure prism, okay, the coordinates, okay, which will be x and y, okay, coordinates at location, okay, locating the coordinate with reference to any surface, okay. Now, what do I want to add here? Okay. All right. Now, still on the hydrostatic pressure for particle, like I said, I already explained. Now we don't have sine alpha, isn't it? In the previous instance, when it is inclined, we have gamma y bar a sine theta or sine alpha. But now, because it is vertical, so no need to have any alpha. This is the centroid, the center of gravity, and this is the center of pressure. Okay. So for vertical and inclined, the center of pressure is below the centroid. Okay. Now let's take this interesting example. And before we take it, let's take just 5 minutes break. Okay, let's take 5 minutes break. Then when we come back, we take this interesting example. Yes, we are back. I realize that Ahmad Fahad Al-Shamri has left. If you leave before the end of the class, you'll be marked as absent. Or you'll be marked not as absent, but having left earlier, okay, in the SIS. So you have to be with me from the beginning till the end, okay? You have to be with me from the beginning till the end. So here is a practical example, very interesting one, which is on hydrostatic force acting on the door of a submerged car. Please note that you remember I gave you two references. I hope you all got the books, okay? Because I use both books in forming my lecture note, in taking my examples, okay? One written by Crow, the other by Yunus Cengel. Yunus Cengel. Cengel or Cengel is a Turkish. Okay, it's a very interesting book. So I use both books. I will try to probably, I have already provided the full references, okay? So there it says you have a heavy car that plunges into a lake. The lake is a stagnant water body, okay? Into a lake during an accident and lands at the bottom of the lake on its wheels. So this is the water at the bottom of the lake on its wheel, okay? And this is the the top of the lake, you can see, okay? The door is 1.2 meter high, that's the height, and 1 meter wide, okay? And the top edge of the door is 8 meters below the free surface of the water. The top is below 8 meters of water. Determine the hydrostatic force on the door and the location of the hydrostatic force on the door and the location of the pressure center. Okay? Of course, water pressure will be acting on the door. So what is hydrostatic force acting on the door and the location of the center of pressure? And discuss if the driver can open the door. You know, the hydrostatic force will be pressing on the door. So will the driver inside the water, inside the car, be able to open the door? That is against the hydrostatic pressure force. Okay, this we will analyze. Okay, so now we have a car in water, submerged in water, completely submerged. Okay, and we are to determine the hydrostatic force and the likelihood of the driver opening the door. Okay, so what are our working assumptions? The assumptions, you know, is that the bottom surface of the lake is horizontal. Okay, and the passenger cabin is well sealed so that no water leaks inside. Because if water leaks inside, then there will also be hydrostatic pressure acting from inside. But if there is no leakage, you have only air, then only atmospheric pressure will be acting inside the car cabin. Okay. Number three, the door can be approximated as a vertical rectangular plate. Okay, so it is like a vertical plate sitting on the bottom on just a vertical plate, not sitting on the bottom because you have the tire also. And the pressure in the passenger cabin remains at atmospheric value since there is no water leaking in. Yeah, this I explained, and there's no compression of the air inside. Therefore, atmospheric pressure cancels out in the calculations. Okay, since it acts on sides of the door. You have the atmospheric pressure from outside, include, you know, with the gauge pressure, and you have atmospheric pressure inside. So we will only be considering the gauge pressure. And the weight of the car is larger than the buoyant force acting on it. Later, after this, we'll explain what is buoyant force. Okay? We'll explain what is buoyant force. So the weight of the car is larger than the buoyant force acting on it. So what we're saying is that the car is in static equilibrium. It is in static equilibrium. And the properties we need here is the density of water, which is 1000, incompressible, so we take it as constant. And we want to find the average pressure gauge, okay? the average gauge pressure acting on the door, and the pressure at the centroid, and the pressure value at the centroid or midpoint of the door is determined by this formula. Okay, because we will have to determine the pressure at the centroid. If you remember, we derived that F hydrostatic pressure is P bar A. P bar is the pressure at the centroid of the plane surface. Okay, so we'll have to find the pressure at the centroid of the door. Okay, the door is plane surface 1 meter width and 1.2 meter high. Okay, so the centroid will be acting somewhere here at 0. Okay, and don't forget the height of the water. Okay, so the centroid will be acting. Okay, this is 8, and this will now be 0.6. Okay, so the total distance now from the top of the water is 8.6. Okay, which is 8 plus 1.5, 1.2 over 2. Okay, so the gauge pressure is rho g8, simple, and the height to the centroid is S, which is 8 meters, plus the centroid, which is B over 2. 8 plus 1.2, simple. So this is the pressure acting, okay, at the centroid. And we simply multiply by the area, which is 1.2 times A. Okay, so this is the resultant hydrostatic force acting, 101 kilonewton, 101.3 kilonewton acting on the door, the hydrostatic pressure acting. Okay, so if we want to represent it, okay, so this is the, okay, it's acting. So we now need to find the center of pressure. Okay, this is the resultant hydrostatic pressure force. We can use FR or FP, whichever one. Okay, all refer to the same thing. Now, to find the center of pressure, we apply the formula for the center of pressure. The center of pressure is directly under the midpoint of the door, and its distance from the surface of the leg is determined by the equation we derived before. That, YP or YCP, okay? Center of pressure. Different textbooks use different notations. Here they're using YP. The other one we're using YCP, all referring to the center of pressure. Okay, it's Y bar plus I bar divided by Y bar A. Okay, divided by Y bar A. So in this case, let's analyze. Y bar is the central distance of the centroid from the top of the water, okay, which is S plus B over 2. Okay, and then I bar, which is the moment of inertia of a rectangle, okay, the centroidal moment of inertia of a rectangular surface, okay, because it is vertical in this case, is BD cubed over 12. Because D is 1, DB, wait, this is the formula, the centroidal moment of inertia, okay, YA, the centroidal axis. Okay, so, and this is Y bar A, I dB cubed over 12. Okay, this is I. Then area for a rectangle, okay, is BD. Okay, area of a rectangle is BD. So when you divide this over this, that is Y bar is S plus B over 2. Distance of the centroid from the top of the water. Okay, so now I over A going to be BD cubed over 12 into BD. Okay, so B can this is for the X, IY, because it's vertical, so it is IY, so it is the other way around. It is B cubed, okay, DB cubed, yeah, DB cubed. So here you have D cancelling out, B cancelling 1, and then you have B squared over 12. That's why here you have B squared over 12, okay? I is DB cubed over 12. Okay, which you can find from the formula at the end. So that is not a big deal. It's not something that you have to derive. Okay. And then when you substitute, you find the center of pressure to be at 8.61. Okay, 8.61, which is below the centroid. Now, about answering whether the person can open the door or not. A strong person can lift about 100 kg. Okay, 100 kg. You know, and 100 kg weighs 981 Newton or about 1 kilonewton. Okay, so a strong man can lift up to, let's say, 1 kilonewton. Now, the person can apply the force at a point farthest from the hinge. You know, a door has a hinge, okay? So let's say 1 meter. When you apply the force, let's say 1 kilonewton at 1 meter, what is the force? What is the moment generated? 1 kilonewton meter, okay? So it's 1 kilonewton times the distance 1 meter. Now, on the other side, because you have the door here, okay? Hydrostatic pressure force acting on this at this height is pushing on the door. While you are inside, you want to open the door, okay? You have to apply a moment that is greater than the one applied by the hydrostatic pressure force, okay? The resultant hydrostatic force acts under the midpoint of the door, and thus a distance of 0.5 from the hinges, okay? About 0.5 from the hinges. And what moment can it generate? It is the moment to be generated is going to be 0.5 times the hydrostatic pressure force, which is 101.3 kilonewton. Okay, so approximately about 50.6 kilonewton meter, while you are generating a counter moment of 1 kilonewton. So definitely you cannot, it is impossible for the driver to open the door because you cannot generate enough moment to counterbalance this moment imposed by the hydrostatic pressure force. Okay, so the best thing is maybe for the driver to open the door so that water can get into the car. By that, the hydrostatic pressure force will reduce from outside, and then from inside it will increase, and then before it becomes before the water level, you know, reaches up to fills the water cabin or the car cabin, he can now open the door because there will be hydrostatic pressure acting from inside as well, which will counterbalance the one acting from outside. So it will be much more easier to open that way than to attempt to open when you have only air inside. Okay, when you have only air inside, you can only generate maximum of about 1 kilonewton, or let's even say 2 or 5 kilonewton, which is still a far cry from 50.6 kilonewton meter. Okay, you generate 5 kilonewton meter, which is extremely lower than 50.6 kilonewton meter. So definitely you cannot open the door, because opening a door is also practical application of moment. You are applying force at a distance, and then the door rotates about a fulcrum. It rotates about a particular point. So that is moment or torque. Okay, I hope it is clear. Attention quiz. We have solved a problem similar to this. So just solve this one. Just calculate the force on the gate. Calculate the force on this gate. Whose height is h, 4 meters, and d is 6 meters. Okay. Calculate the force on the gate and locate its point of action. Okay. So unfortunately, this is online. Hence I cannot look at exactly what you do. So, but it's simply, you know, the same thing we did before. Okay. It's following the same thing we did before. Okay. But and the gate dimensions are 4 by 2 meters. The height is 4. So here h equals 4, d equals 6. The gate is meaning is rectangular, so it is 4 by 2 meters. Okay? 4 by 2 meters. Okay, so you simply determine the pressure force acting. First, the pressure acting at the centroid. Okay, pressure acting at the centroid, which is gamma h, and h here because the fluid is water, so the unit weight 9810, and h now is going to be the distance 6 plus up to the centroid 4/2. Okay, which is this point. Okay, this is 2, which is 4/2, then plus 6. So there you get the pressure, and to get the pressure force or the resultant hydrostatic force, PA, okay, the area, this you get it from this one, and the area is 4 by 2. Simple. Okay. And to get the center of pressure, YCP or YP, simply Y bar plus I over Y bar A. Okay. And then Y bar, don't forget, is the distance from the centroid to the top of the water surface, which is 8. Okay, so this is 8 plus I, which is dB cubed over 12 times Y bar. Y bar is 8 times the area 4 by 2. Okay. Then you substitute dB. D and B here. D here is the depth of the panel, which is 4. D is the width, the breadth, okay, which is 2 to the power of 3. Okay, so this will give you the center of pressure. Very simple. Okay. Now let's take another example. The first one we looked at in vertical plane panel. Now we want to look at inclined submerged panel. Okay, so we have to find the force also. Force to open an elliptical gate. So here the problem statement goes as an elliptical gate. Gate is simply, you know, just like the word gate, you open the gate to allow cars to come in, people to come in, and what have you. Here, you open gate to allow water. Okay, it's water gate. You open it to allow water to go in. Okay, so you have an elliptical gate. covers the end of a pipe, 4-meter in diameter. So this is the pipe, which is under atmospheric pressure, and this is the gate, which is elliptical. Okay, and ellipse. This is an ellipse. Okay, it has major and minor axis. It's different from a cycle because it is like elongated. Okay, so this is an ellipse. The area of an ellipse is AB, and this moment of inertia is pi AB cubed over 4, okay, for an ellipse. So you have this shape covering the pipe, okay, and it is inclined. It has a hinge here. The gate is at the top. This is the hinge. What normal force F is required to open the gate when water is 8-meter deep above top of the pipe? Water is 8-meter deep. So what normal force is required to open the gate? Okay. So this force has to overcome the hydrostatic pressure force, isn't it? It has to overcome the hydrostatic pressure force. And the pipe is open to the atmosphere on the other side. Neglect the weight of the plate. By neglecting the weight of the plate, otherwise it has to be included in the analysis. Okay. And here, water pressure is acting on an elliptical gate, and these are the properties of water. And assumptions neglect the weight of the plate and neglect friction between the bottom of the plate and the pipe wall. Otherwise, we have to show the pressure, the friction force. Okay, remember chapter 8 of statics also. Okay, because there is friction. Whenever you have two bodies in contact, friction force exists. Okay, so to generate ideas and make plan, we have to calculate the resultant hydrostatic force. Okay, and find the location of the center of pressure and draw an FBD of the gate and apply moment equilibrium about the hinge. So this is the pressure acting at the depth of the centroid. Okay, the pressure acting at the depth of the centroid is gamma H, okay, or gamma Z. Okay, and Z here is the distance from the top to the centroid. Okay, from the top of the water to the centroid. The ellipse, the pipe is 4-meter in diameter. Okay, so the centroid will lie at midway, which is at a point 2 meters. Okay, so this is 8 and this is 2 meters. So total to the distance to the height of water to the centroid is 10. Okay, so that's why we have this 10. Okay, and from there we find the pressure for acting at the centroid of the electric gate. Okay, 98.1 kilopascal. And the area of the elliptical panel is pi AB. A is the major radius and B is the minor radius. Okay, we were based on the information we have. This is vertical. Okay, this is 5 meter. Okay, and the height is 2 meter. Okay, so A is 2.5, that is 5/2, and B is 4/2, which is 2. Okay, so the area is pi times 2.5 times 2. Okay? So to calculate the resultant force or resultant hydrostatic force, we use the pressure acting at the centroid multiplied by the area. So this is the pressure force, 1.58 meganewton. Now, to find the center of pressure, this is the formula. Okay, so this is the formula for the center of pressure, and this is the moment of Y. Y bar in this case is the slant height, slant distance. Now, how do we find Y bar? Remember, this is different from the vertical panel. For the vertical panel, Y bar is simply 8 plus 2. But for the inclined or slanting or tilted panel, Y bar has to be projected. Okay, this is the okay. So this is Y bar at this point. Okay, distance here. Okay, this is Y bar. And how do we find it? How do we find Y bar? Very simple. This is 5. This is 4. And definitely this is 3. So let me sketch it here. Sketch it here. Okay. If this is 4, this is 5, and definitely this is 3 by Pythagoras theorem. Okay, and then this is 8. If this is 8, these two triangles are similar. Okay, they are similar. If this is 8, then definitely this is 6 and this is 10. Okay, and what is now the distance to the centroid? The centroid is lying here, which is at 2.5. This is 2.5. So from now here to here, I have 2.5 plus 10, which is 12.5. Okay, so in this case, Y bar is equal to 12.5 meter. We simply use similar triangle. Very simple. Okay, use similar triangle. This is 5, this is 4. So from here to here is definitely 3. Okay, and then if this is 8, then definitely this is 6 and this is 10. Now this is for Y bar, and then for I we get the formula, which is this. Okay, so we simply substitute to get moment of inertia, and then find the center of pressure. We substitute all the values here. Okay, which is 0.125 below the centroid. Okay, below the centroid. The centroid is at 2.5, so 2.5 plus 0.125, which is 2.65. Now we draw the free body diagram. We have the hydrostatic pressure force acting at the center of pressure at a distance of 2.625 from the hinge. Hinge is having two reactions, if you remember from your statics, okay? Horizontal and vertical, okay? And this is the force that we want to overcome. We want to open the gate. The force has to be at least equal to the pressure force to be able to push it, okay? So we just take moment about the hinge. We don't need to find hx and hy. We just, because when we take moment about the hinge, hx and hy will vanish. Okay, and then we can find f. So taking moment about the hinge will be equal to 0. Okay, we now find, this is due to the pressure force, which is clockwise. Okay, clockwise moment equal counterclockwise moment, or the sum of moments equal 0. Here we are taking counterclockwise to be positive and clockwise to be negative. So this is the pressure force, and the distance moment arm is 2.625 minus F times the distance to the hinge is 5 meters, and F is 809 kilonewton. Okay, so you need 809 kilonewton to be able to open the gate. Okay, this amount of force applied here to be open the gate. You can see that the force needed is less than the force of the pressure force. Okay, that is because of the moment, because you are generating moment about the hinge, and the farther you are from the hinge, the more moment you generate. Okay, and the closer you are to the hinge, the more force needed. Okay, so if you can see, the pressure force is closer to the hinge. Okay, so applying the force further away from the pressure force, definitely you will require less force, okay, to counterbalance the moment created by the pressure force, Fp. I hope it is clear. Any question on this? It's a very interesting example as well. Now this is another attention quiz, which is saying what force at point G is required to prevent the gate from opening, given that, okay, to prevent the gate from opening, given that D equals 7 and H equals 5. So here, you should try to solve all these attention quizzes yourself, because they will demonstrate whether you truly understood the example I solved in the class, okay, or not. Is that clear? So here also you have a gate and a hinge, and the specific gravity of the fluid is 0.9, meaning it is not water. Okay, the specific gravity of water is 1. Okay, anything less than 1 or above greater than 1, it means it is a different fluid. Okay, so the liquid here is not water, because its specific gravity is 0.9. Okay, so what force at point G is required to prevent the gate from opening? Okay, so as it is here, water will push, hydrostatic pressure force will be acting somewhere here at the center of pressure. So it will try to create moment about the hinge to open the gate. So what normal force do you need to balance it? Okay, what force do you need to apply to prevent it? It's similar to the example I solved, except that this one is not or it's not inclined. Okay, it's not inclined. So all you need to do is to find the acting at the centroid. Okay, and here the gate dimensions, you have 5 by 2. Okay, so you need to find the pressure acting at the centroid. Okay, P bar, okay, which is gamma times the H is going to be 7 plus, from the height, from the top of the liquid to the centroid, which is 5/2. Okay, and then you find the pressure force, okay, times the area. The area here 5/2, and then you find the center of pressure. Okay, you find the center of pressure using the formula. Okay, once you find the center of pressure, and then you now draw the free body diagram of the hinge and apply the equations of equilibrium. This is a hinge. Then you have Hx, you have Hy, and you have this is the centroid, and this is the center of pressure, where you have the pressure force acting, and you need the force, the normal force that will prevent the gate from opening. Of course, here also we are neglecting the weight of the gate, because if we don't neglect the weight, it has to be included. Although even if it is included here, when we take moment about the hinge, let's say O, the weight is going to disappear because the weight is going to pass through the hinge. Okay, so it wouldn't make any impact. Okay, so the only unknown will be F. Okay, so you find F. Very simple. Is it clear? We will have quiz next week. It's just because I have not, I didn't feel well. I would have prepared it this week, but next week definitely we will have a quiz. And then I will grade your major 1 from today. Hopefully, I hope to finish it tomorrow or even today if I have enough time. Okay? And then I will post the grades. Okay? And then, of course, like I said, we have like about 6 hours the first week that we missed, and then about 3 more hours. So total of 6 hours. We make up lectures. So I will try to make up these lectures as time progresses gradually. Okay? Let me see what you are writing. So now I have 14 attendees, one person missing. So, yeah, no quiz today. We will take quiz at the next week. Okay, sorry for interrupting, Doctor. But major exams start after 1 hour from now. Yeah, if you have major exam 1 hour from now, that is at 11. You can leave 1 hour before the exams. Okay, you leave 1 hour before the exams. Let's go on. Now, in all this, you see, what we have considered are plane surfaces, either horizontal, vertical, or inclined. But the body surface is plane. Now we will consider curved surface, because more often than not, as engineers, we calculate pressure forces on curved surfaces when we are designing components such as tanks, pipes, and curved gates. Okay. In many practical applications, submerged surfaces are not flat. This is a dam, you can see it. It is curved. Okay, it is curved. So we need to learn how to find the hydrostatic pressure forces, the hydrostatic forces on curved surface. For a submerged curved surface, the determination of the resultant hydrostatic force is more involved, because it typically requires the integration of the pressure forces that change direction along the curved surface. This is very difficult to achieve. Hence, the concept of the pressure prism in this case is not much help, either because of the complicated shapes involved. So the easiest way to determine the resultant hydrostatic force acting on a two-dimensional curved surface is to determine the horizontal and vertical components separately. Okay, so rather than integrating around the surface because it is curved, if you remember, when finding even the centroid, of a curved surface, we need to integrate. But integrating here will give us, a lot of uh, will not be very easy, okay, in this case. So the best way is to find the horizontal and vertical components of the hydrostatic pressure force and then find the resultant hydrostatic force acting from the horizontal and vertical components. So this is done by considering the free body diagram of the liquid block enclosed by the curved surface and the two plane surfaces. This is a curved surface from A to B. You can see that, okay? You have a liquid on top exerting pressure on the curved surface. Okay? Now, if you draw the free body diagram of the liquid block enclosed by the curved surface, okay, one horizontal and one vertical, passing through the two ends of the curved surface as shown. Okay, this is the horizontal projection of the curved surface. Okay, because this is acting on this. Okay, so when you project it, okay, and this is the horizontal component of the hydrostatic forces acting. Okay, so you have the vertical component Fy and the horizontal component, and the two are different because for horizontal you have uniform pressure distribution. For vertical, you have non-uniform pressure distribution, and we have already analyzed how to find each one of the pressure forces before examples. Okay, so this is the pressure resulting from and this is the weight of the liquid acting. Okay, so this is counterbalanced because according to Newton's third law, action and reaction are equal and opposite. So the vertical surface of the block considered is simply the projection of the curved surface on a vertical plane. Okay, and the horizontal surface is the projection of the curved surface on a horizontal plane. Okay, so the resultant force acting on the curved solid surface is then equal and opposite to the force acting on the curved liquid surface. You have Fx due to the hydrostatic pressure acting on the surface. It has to be resisted by the curved surface by equal but opposite force, Fh. The same thing, this Fy has to be resisted by equal but opposite force by the curved surface, according to Newton's third law of motion. And then you can find the resultant, okay, the resultant force, Fr. Okay, so Fh is equal to Fx, and Fv in this case, Fv is resisting the vertical hydrostatic force as well as the weight of the fluid. So Fy plus or minus u. Here plus because they are in the same direction. As we are going to see other cases, there may be an instance when they may not be in the same direction because this is vector addition. Okay, if they are not in the same direction, you subtract. Okay, we'll expatiate this more. But for the horizontal force, Fh is equal to Fx. But for the vertical one, because of the weight component vertically downward, so the vertical force acting or resisting the hydrostatic force has to also resist the weight. Okay, the weight is contributing, okay, to the force acting vertically downward, and all these have to be resisted by the vertical force of the curved surface. And the force acting on the imaginary horizontal or vertical plane surface and its line of action can be determined. Okay, determine its line of action. Okay, because once we have FH and FB, we can determine FR and its direction. Now, calculating the magnitude of the resultant force is FR equal, the normal formula of finding the resultant force and the normal formula for finding the direction, okay, angle, which is alpha in this case, and the exact location of the line of action of the resultant force, e.g., its distance from one of the end points of the curved surface, can be determined by taking a moment about an appropriate point. If we take a moment about either A or B, we can find the distance that FR is, acting at. Okay? And these discussions are valid for all curved surfaces, regardless of whether they are above or below the liquid. Oh, it's about to be up. And still, now, like in this case, you can see that Fy is in opposite direction with W. So we subtract Fy minus W in this case. Okay? And in this case, you can see if we have a semicircle, then definitely the resultant force is passing through the center because all the forces have to pass through the centroid of the semicircle, as well as the resultant force is passing through the center in this case. Okay. Then when you have two different fluids, okay, like water, we treat them separate. Okay. In this case, we find the resultant force for that part lying in water, and we find the resultant force for that part of the planes of lying in oil. And then overall hydrostatic force is the summation of these two resultant forces. Okay. We'll take example on the curved gates. Okay. All right. So see you in the next class.